Well, good afternoon and welcome to this session on NSX. Let me just say a couple of words about the title. Actually, before I even say that, I'll warn you, I may lose my voice before the end of the session. I woke up unable to speak this morning, so things have improved in the last couple of hours, and hopefully I'll see it through to the end of the hour. I'll also say I have a tendency to speak fast, especially when I'm excited, and I'm very excited about this topic, so I apologize in advance if I speak too fast, but I'll do my best. I'm Bruce Davie. I'm one of the principal engineers in the Networking and Security Business Unit at VMware, and I've been working on NSX for a few years now, since back in the days when I worked at Nicira. And so what I'm going to talk about today is quite a forward-looking talk. When I came up with the title, it's probably not the best title I could have come up with, but it's not so much advanced in the sense of being really difficult, more in the sense of these are some of the topics that you won't necessarily hear about in other sessions, maybe because they're things that are still on the roadmap or still getting developed. I work on the architecture of the product, so this is a lot of stuff that's very close to my heart, the sorts of things that we've been developing, some of which are in the product today, but some of which will show up in the future. So with that, I'll put up the standard disclaimer slide. This slide is probably more true for this session than almost any other session you'll see this week, that this presentation definitely contains features that are currently under development, etc., etc. So what I hope you'll get out of this session is you'll get a bit of an update on the latest NSX capabilities, and there are a lot of other sessions on NSX, so I can't pretend to cover everything that NSX does, but I will cover some of the high points. But mostly I'm going to give you some insight into the future of NSX and where the product is heading. And I hope that you'll leave here really understanding what network virtualization can do so that you'll really understand the technology in a sort of a deep way and understand whether it will address problems in your network or in your data center. So it's possible you'll go out of here thinking, actually NSX doesn't solve any problem that I have, which would be okay. It wouldn't be my first objective, but that would actually probably be a good use of time, even if you can conclude that it doesn't help you. But hopefully you'll go out of here realizing that it's exactly what you need to solve some problems that you have. So this is how I'm going to approach the talk. I'm going to start, because this is an advanced topics talk, I'm going to very briefly cover the basics of network virtualization, tell you what it is and how we've implemented it. And I will do that very quickly, relatively speaking. How many people here have been to at least one session on NSX this week? Okay, good. Most people. For those who didn't put their hands up, you'll get some introduction to the basics as well. But for the rest of you, this is really just a level set. So anyway, after I've done the introduction, then I'll talk about some of the sort of newer features that we're working on, including things like how we integrate virtual networks with physical networks. And then I'll talk a little bit about some new work that we've done in terms of how we encapsulate packets when we send them across the physical network and the types of network packet encapsulation that we use to achieve virtualization, which is a topic that's, I guess, very exciting for people who live in the physical networking world. How many people here would say they're traditional networking people? Most people. So you'll probably get excited about encapsulations then. I myself am an old networking person. So I'll talk a bit about that. And one of the things that we're enabling with these new approaches to encapsulation is some service chaining. So I'll talk a little bit about that, and that's another kind of hot topic. And then finally, if time permits, I'll say a little bit about where we're going on enabling network virtualization across multiple sites, across multiple data centers. Today, I think almost all of the deployments of NSX have focused on virtualizing individual data centers. And it's our long-term plan to be able to stretch that across multiple data centers. And so I'll say a bit about that towards the end as time permits. So without further ado, let me just remind you or explain, if it's the first time you're hearing this, what we mean when we say network virtualization. Now, network virtualization is best understood as it relates to server virtualization by way of analogy. Now, when you virtualize a server, you start off with some basic underlying hardware, and that hardware has fairly generic properties, has an x86 instruction set, it has some memory, it has some I/O, and then you put a software layer on top of that basic hardware, and that virtualizes it and then above the software layer, the hypervisor, you can create virtual machines which are completely decoupled from the underlying hardware. They're decoupled to such a good extent that you can pick up a virtual machine and move it somewhere else. You can swap out the hardware and bring in new hardware and keep the virtual machine running. So that's what I mean by decoupling, and that's one of the first things I want you to think about when we talk about network virtualization. The second thing about a virtual machine is that it faithfully reproduces all of the properties of a physical machine. So a virtual machine has the same instruction set, it has memory, it has I/O, it exactly faithfully reproduces a physical machine, and so much so that when you run an application inside a virtual machine, it doesn't know that it's not running on physical hardware. So faithful reproduction of the underlying physical thing is another property of virtualization. So those are the two things that we strive for in network virtualization: to decouple network services and network features from the underlying physical hardware in such a way that the physical hardware could be swapped out and replaced. You could move virtual networking functions from one place to another, perhaps move them even to a different data center without changing the network functions. You could do all of that in a way that's decoupled from the underlying hardware, and at the same time, we faithfully reproduce everything that you would expect to get from a physical network. So that means layer 2, layer 3, L4 through 7 services, firewalling, load balancing, etc. It's a complete network stack. Now, this was a pretty bold objective. This was our objective when we started Nicira, and at the time that I joined Nicira, we had about 45 engineers. And this idea that this little tiny company was going to virtualize all of networking while, down the road from us, 20,000 people were working on Tasman Drive building physical networking gear, we felt this was a very bold objective. But the way we were able to achieve it is in large part by making NSX a platform which we extend with the capabilities of our partners. So I'll talk a little bit today about our partner ecosystem, but I also want you to think about NSX as not just a single product, but actually a platform enabling an entire ecosystem so that we can virtualize all of networking. So now that I've told you what we intended to do with network virtualization, let me just spend one more slide explaining how we've built the system, and this will again provide the background for a lot of the more advanced topics. So if you've seen a presentation on NSX before, you might have seen a slide a bit like this. We start with a set of hypervisors, and as you probably know, NSX can support multiple different types of hypervisor: vSphere, KVM, Xen today, Hyper-V in the future. And inside every hypervisor, there's a vSwitch. That vSwitch is really the place where we can implement pieces of network functionality, and the vSwitch is the place that really processes packets as they're coming in and out of virtual machines. But the real brains of the operation is the controller. And the controller is actually a cluster of machines. It's a scale-out, highly available system. And that cluster stores in its memory representations of virtual networks. Those virtual networks are created, and virtual machines are attached to those virtual networks by the use of API requests coming into this centralized controller. So the NSX controller is a centralized point of control which receives API requests that can create, monitor, manage, modify virtual networks. And the controller then looks down at the hypervisors under its control, looks at where the virtual machines are currently located, and programs vSwitches to instantiate these virtual networks. In this example here, we've got a couple of virtual machines, a bit of firewalling, some L2, some L3. All of those properties of the virtual network are requested through the northbound API, and then the controller calculates how to go and program the vSwitches to instantiate those virtual networks. If a virtual machine moves, it recalculates what needs to happen and goes and reprograms a virtual switch to maintain the consistent picture of that virtual network. Typically, sitting above that northbound API is a cloud management platform. This is often something like, say, vCloud Automation Center or Cloud Stack or OpenStack. So we're kind of agnostic about what sits up there, but it has to be something that can generate those API requests. So this is a big shift in terms of how we think about networking. Networking used to be about going and configuring boxes. and used to be done through CLI. Now, the creation of networks is something that's done through API requests. The fact that it's done through API requests into a single centralized location, a logically centralized location, means that you can now automate the process of setting up networks. So, for example, I can click a button in the cloud management platform and spin up an entire virtual network that meets some objectives. This is exactly what we do inside our engineering organization at VMware. Every time a developer wants to create a test network to test out his code, he pushes a button that brings up the standard test network. It has something like 15 virtual machines in it, connected into some topology. With one push of a button in the cloud management platform, some very large number of API requests are generated, and the controller then goes and spins up the virtual network by programming a bunch of vSwitches, and at the same time the cloud management platform also brings up the virtual machines, and the entire thing is created without a human ever touching anything other than the developer who pushed the button on the cloud management platform. So it's a fantastic way of automating the provisioning of networks. Now there's a couple of other pieces to this picture. We need to get traffic across the physical network somehow, and we need to do it in a way that decouples all of these virtual network services from the underlying physical hardware. So we do that by tunneling packets. That is to say, we take the packets that were generated within a virtual machine, we wrap them up inside an external packet header, and then we send that packet across the physical network. So the physical network, all it's doing is forwarding packets from one hypervisor to another. So this is how we decouple the services that NSX delivers from the underlying physical hardware. The services are delivered in the vSwitch. The job of the hardware is just to move packets between one hypervisor and another. Inevitably, we need to get data in and out of the virtual networks, possibly in and out of the data center. So we have a couple of ways of doing that. We have the NSX Edge, which is a x86-based appliance that runs our software and can terminate tunnels and is under the control of the NSX Controller. It can take packets coming in off a physical interface from the outside world and then map them into a virtual network. We also partner with a large number of switch and router companies to provide this hardware approach that does similar capabilities to the NSX Edge, but does it in a hardware switching form factor at very high throughput and high port density, and I'll talk more about that in a few minutes. So that is your super quick introduction to NSX. Hopefully not too boring for those who've heard it before. Any questions before I move on to the sort of the forward-looking part of the presentation? I'll take one or two questions if they're quick, and we do have microphones. Just raise your hand. We have one right in the front row here, and the microphone is not on its way because it's not here. Okay, so just ask your question and I'll repeat it.
You mentioned before only the standard switches. What about the distributed switches?
The question is, what about the distributed switches? So you can think of the VMware distributed switch as sort of almost like a version 1 of NSX. It takes vSwitches and creates an illusion of a bigger switch across multiple hypervisors. NSX just takes that to a whole other level with a much higher degree of distribution and a much greater feature set. So at some level, VDS is sort of the basic building block that sits inside the vSphere hosts as the vSwitch, and then we empower it to do much more using NSX. Are there any other questions? Okay, I'll take one more. What about performance? Yeah, it's a fair question. So let me just touch briefly on performance, and I'll come back to it later. So if you have a hypervisor today, your packets are almost certainly passing through the vSwitch, and you've probably been doing that happily for years without noticing any performance problems. I hope that's the case. So the vSwitch receives the packet as it leaves the guest and goes into the hypervisor, and then it does some processing and sends it out on the physical network. That's what vSwitches do. Most of the cost of doing that is actually getting the packet from the guest into the vSwitch in the first place. Once you have it there, sitting in memory, it's not that expensive to do a few other things, like put on an extra packet header to tunnel it, or a firewall rule. So there is some incremental performance effect of running these advanced services, but it's quite small. And we do characterize the performance intensively. We do a lot of tests on performance. And so today we can run packets through the vSwitch applying a decent number of, say, firewall rules at 10 gig line rate. So the performance is pretty good. and I'll say a little bit more about that later. There's actually some ways in which the performance here is superior to some physical alternatives. Okay, I'm going to move on. If there's somebody who's like an official staff person here, it would be great if the microphones showed up before we take more questions. Okay, so I'll just move on. And so now I'm going to start going into the advanced topics piece. So hopefully, you'll all come out of here having learned something. You can pat yourself on the back for having survived an advanced talk. As I say, I don't really think this is rocket science. It's more of the things that are a bit off the beaten path or a bit more out in the future. So I've been working on this part of the product for a couple of years now, which is how do we get NSX to talk to physical switches so that we can bring traffic from the physical world into the virtual world using a hardware switching form factor. The reason for doing this is to create virtual networks that have both physical endpoints and virtual endpoints. So we've created a protocol called OVSDB. It's actually part of the Open vSwitch project, and we've used that as the way that we communicate between the NSX controller and third-party switches. And there's about half a dozen switch vendors who've implemented this, with more coming every day. So just as before, we create virtual networks by making API requests into the controller. In this example, the virtual network has some virtual machines on it, and it has some physical machines. So we want to build, in this example, a layer 2 network that has both physical endpoints and virtual endpoints. We tell the controller that's what we want, and the controller starts communicating with both the hypervisors and the physical switches that it's communicating with using OVSDB. Now, OVSDB is actually a database protocol, and there's a little tiny database sitting on the switch. It's a piece of open source code that our partners can leverage, and that database is used for both the switch and the controller to exchange information. So, for example, the controller knows where the virtual machine MAC addresses are, and so it takes that information and writes it into the database. The physical switch knows the MAC addresses of the physical hosts, which it learns through conventional means, so it writes that information into the database as well. So both the switch and the controller are looking at this database, and they build up a shared view of the physical world and the virtual world, just enough to enable this physical switch to participate in these networks. And eventually, there's a bunch more information goes back and forth, and tunnels can be built between the physical switch and the hypervisors. These are VXLAN tunnels. And at this point, we can now forward traffic from the physical host to the virtual machine and vice versa, meeting the requirements of the virtual topology that was created through the northbound API. So this is something that we actually announced at VMworld a year ago. So we've been working on it quite a lot since then. And probably the biggest thing that we've done in the last year is starting development on enabling a layer 3 routing model in addition to the bridging picture that I've shown here. So what we're doing now is we're creating a logical topology similar to what's shown on the left, where you could now have, say, virtual machines in one subnet, some physical machines in a different subnet. You could build much more complex topologies than this. This is just a simple example. So we take that logical topology, we tell the controller that's what we want, and then we create it using the physical devices shown on the right-hand side there. And in the next slide, I'll show you a little bit more detail about how this works. But essentially, the controller is going to create a fully distributed logical router. Now, you may be aware of the fact that NSX creates a lot of distributed services. What this means is that there will not be a single device in the network that's performing routing for this logical network. It'll be done by a number of different devices. Some number of vSwitches and some number of hardware switches will collaborate to implement this distributed router. So I'm going to show you that in a very simple example. So let's imagine that this virtual machine has decided it wants to send a packet to the physical machine, which, as you can tell, is in a different subnet based on the IP addresses. So the first thing the virtual machine is going to do is it's going to send an ARP request for its default router. And it presumably learned the address of its default router from DHCP or configuration. So it sends its ARP request, and that ARP request gets intercepted by the vSwitch. The vSwitch has been programmed by the controller to recognize what it should do. So when it sees this ARP request, it says, okay, I can act as the logical router for this network, so I'll take your ARP request and I'll reply to it. And so at this point, the virtual machine knows how to talk to its router, and it can now send a packet to the router. Now, of course, it's going to hit the vSwitch. The vSwitch has to figure out what to do with the packet. So the vSwitch will now ARP for the destination of the packet. And the destination of the packet is that physical server off on the right-hand side. So the ARP packet goes across to the physical switch. It's sent inside a VXLAN tunnel. When it reaches the physical switch decapsulates it and sends it out to the physical world, where it looks exactly like a standard ARP packet coming from a traditional router. So the physical device gets this and replies to it. It goes back into the physical switch, which will then encapsulate that packet back into a VXLAN tunnel and send it back to the vSwitch. So at this point, the vSwitch knows enough information to forward data to the destination. And so now data packets flow. By the way, I think this is the most sophisticated PowerPoint animation I've ever done, so I hope you enjoyed it. Thank you. Best audience ever. So now, at this point, you might think that the vSwitch is doing all the routing. But if I had time, I could now run this example in the opposite direction, and all the things that were getting done by the vSwitch, all that ARP processing, would actually be getting done in the physical switch. So the physical switch is going to handle ARP processing and doing the routing of the packets for packets going from right to left, whereas the vSwitch is handling the ARP processing and the routing for packets going left to right. So that's what I mean by a distributed router. In this example, the router is collaboratively implemented by two devices. In a more common scenario with more endpoints, we might have 10 hypervisors and 3 physical switches. They would all be collaborating in implementing this distributed logical router. So I think this is pretty cool. It's enormously powerful in terms of how it enables us to scale NSX. It kind of gets back to the question we had earlier about performance, that one of the things about NSX is because we implement so many services in a fully distributed way, you don't send a packet to a box to get it processed. You send it to the vSwitch, where it gets a bit of processing, and then it gets tunneled either to a physical switch or to another vSwitch, where it gets a bit more processing. And so we can scale out a lot of these services to fully utilize all the capacity in the data center. This is extremely effective in the case of firewalling, for example, where you can implement a distributed firewall that uses a little bit of capacity on hundreds or thousands of hypervisors, and you can get firewalling capacity that scales as you scale up your data center. So as you add more workloads, instead of going and buying more and more firewalls, you're already putting in more servers to run those workloads. You get firewalling built in the vSwitch. So this is pretty powerful. Right, everything on that slide I said previously, so you can refer to that at your leisure. So now, just a few more things that are coming down the road. By the way, I don't think I ever explained the acronym VTEP. Does anybody want to take a shot at expanding VTEP? There we go. That man took a selfie with me earlier. He's obviously been studying NSX. He said correctly that VTEP stands for VXLAN Tunnel Endpoint. So that's what we use to refer to these hardware devices that terminate VXLAN for us. Strictly, we should call them hardware VTEPs. So we have a few more things coming down the road. We've developed a tunnel monitoring approach using the bidirectional forwarding detection mechanism. By the way, this slide is very heavy on acronyms. I apologize for that. So we use BFD to monitor the health of tunnels. We use this extensively in NSX, and we've just recently added the capability to test the connectivity between a hardware VTEP and another node in NSX so that we can make sure we have connectivity and we don't send packets into black holes. We also are exploring the possibility of configuring access control lists on hardware switches using NSX as the controller so that you could have a consistent security policy across a network that's a mixture of physical and virtual, and implement your security policy centrally by programming NSX, having it implement that both in our distributed firewall and using the access control capabilities of physical switches. Similarly, once you have that capability, you could think about doing things like setting the diffserv code point to enforce some quality of service. And we're even starting to look at enabling things that are not switches or routers, but things like application delivery controllers or load balancers to sit in that position of a hardware VTEP and interact with NSX directly over VXLAN tunnels. So we've got a lot of work coming down the road in terms of how we interact with physical devices. Now, speaking of interacting with the physical world, another question that comes up a lot when we talk about running virtual networks on top of physical networks is a lot of people say, how do you manage congestion in the physical network? And which is a reasonable question. So, we have a lot of different answers to that, but one answer is try to build a physical network that's not likely to get congested by putting in a lot of capacity. That's generally a good idea. Just like when you build a data center, you put in enough servers to make sure you have enough capacity to run all your workloads. You can't magically create new capacity on demand. So it's a good idea to put enough capacity in the physical network. But sometimes things happen that cause congestion in isolated parts of the network, even though the network as a whole may be well provisioned. And one example of this is what we call elephant flows. So elephant flows are very large, long-lived flows of traffic, typically caused by something like a large file transfer. And they last long enough and go at high enough bandwidth to induce some congestion on some links, particularly if, say, there are multiple elephants and they happen to converge onto a single link. So in this case, the other flows, which we call the mice, are the little latency-sensitive flows that find themselves stuck in traffic behind the elephants. And so what we'd like to do is to try to isolate the elephants and the mice so that the elephants don't stomp on the mice, which is obviously not good. So we've done a bunch of work on addressing this problem, and we realized that you really want to split it into two pieces. First of all, you have to detect the elephants, and then you have to do something about them. That's pretty obvious. So the vSwitch is extremely well positioned for detecting elephants. It's already seeing every packet. So by looking at the frequency with which packets are arriving for a particular flow, we can determine if a particular flow constitutes an elephant. And roughly speaking, we decide that a flow is an elephant if it's sending at a high bandwidth for a sufficiently long period of time. If it doesn't send for a long period of time, there's not much we can do, and it probably won't cause congestion. If it's not sending at high bandwidth, it's definitely not an elephant. So that's how we detect elephants, roughly. And then once we've done that, there's a lot of different things that we can do to mitigate the effects of elephants in the data center or in the network, physical network. So one of the things that we can do, for example, is mark the diffserv code point in the outer header of the packets going through the physical network so that elephants and mice can be put into different queues. And that way we can make sure that the elephants are isolated from the mice, and I'll show you in a second how well that works. Another thing we could actually do is maybe route the elephants over one set of paths and the mice over a different set of paths. And there's even the possibility you could take elephant flows and chop them up into smaller flows, so effectively converting elephants to mice, which is obviously something you can only do in the virtual world. So here's our results. This is before we've done anything to mitigate elephant flows. This was done using a prototype. This is not available today, just to be clear, but we prototyped this using Open vSwitch and working with our friends at Cumulus using their switches, but probably any reasonable switch would work. So initially, the green shows the elephants getting a lot of bandwidth, and then the blue, you should read the scale on the right-hand side, is showing the latency experienced by the mice, the short flows. And you can see that as long as the elephants are present, the mice are experiencing relatively high latency in the 3 millisecond range. When the elephants go away, the latency for the mice drops. So when we turn on elephant flow detection and put the elephants and mice into different queues, we get this result. So now you can see that the mice stay down at half millisecond latency independent of whether the elephants are there or not, which is exactly what you want. So we've successfully identified the elephants and then marked them and then put them in a different queue. So now the mice go through with low latency, and you can also see the elephants continue to get high bandwidth because they're getting all the bandwidth that's not being used, and the mice themselves don't use that much bandwidth. So it's sort of a win-win. The mice are happy, the elephants are happy. Well, I'm happy to take the occasional question as we go. So if you have a burning question, yep, there was. Go ahead. Oh, the microphone is coming this time.
What about redundancy and multiple connections, spanning tree, interchannel? Because we don't do only one connection, as you showed me.
Okay, so that was a fairly large compound question. I'll try to distill that down. So what about redundancy and spanning tree? So I'll tackle that part first. So first of all, we don't really require anybody to run spanning tree. In fact, we discourage people from running spanning tree. So most modern data centers of a large scale are now getting built with layer 3 networks rather than layer 2. So increasingly we're seeing people build data centers where the L2 to L3 boundary is the top of rack, which means you don't need to run spanning tree because it's a single link between the top of rack switch and the hypervisors. If you choose to run spanning tree, that's kind of your business, and we don't have an opinion about it. All we really ask is that the physical network should be as resilient as you can make it so that packets can get between the hypervisors. Now, as people build layer 3 networks in this sort of leaf spine architecture that's becoming very popular, you'll see there's often multiple paths across the backbone from one top of rack to multiple different spine switches. And so those kind of architectures give you a lot of multipathing, a lot of redundancy for link failures. And so at that point, the only thing you'd probably be concerned about would be redundancy between the top of rack and the hypervisor, which could be done using something like MLAG. And again, we don't really have a strong opinion about that. As long as the switch supports it, then we can support it from the hypervisor, and NSX can use both of those links. Okay, I think I'll keep on going since time is getting away from us. But again, if you have a burning question, you should feel free to try to get my attention. So tunneling, I want to talk about this briefly. As I say, I'm an old networking person. I've probably done more work on tunneling protocols than I care to mention. Some people know me as somebody associated with MPLS, which is effectively a form of tunneling protocol too. Networking people love this stuff. I actually think it's becoming increasingly unimportant, but I'll give you a bit of insight into what we've done recently, because the details do actually matter. In particular, since we're taking hardware devices and getting them to talk to hypervisors, we need a tunnel format that works for both hardware and software. So VXLAN was kind of one of the first versions of that, but it's not the last word in tunneling. You also want to make sure that equal cost multipath works. So that's just relative to my previous question. If you have multiple different layer 3 paths across the backbone of your data center network, you'd definitely like to use them all. So you want to make sure there's good entropy in the packets. I do see there's a burning question at the back there. So
Thank you. On the elephant flow before, how you put them in different queue? All of them going through the same physical layer. So I'm a little bit confused. How you put them in different queue?
So I think if I understood correctly, the question is, how was I able to isolate the mice from the elephants since they're going over the same physical network?
Exactly.
Great. So the way we did it was by marking the packets using the outer header of the packet to say, these packets have one particular diff-serve code point, one particular QoS treatment, these other packets have a different marking, and then on the physical switches, we've configured queuing in such a way that there are 2 different queues. So you can think of the sort of the a priori configuration is have at least 2 queues set up on your network that can be where you can direct packets into one queue or another based on the diff-serve code point.
So you use the QoS queue on the physical layer, so you have to have the QoS already configured on physical.
That's correct. You need to have some basic QoS capability enabled on the physical layer, and then our job in the virtual layer is to recognize the elephants and direct them into the right queue.
Okay, thank you.
Okay, great. Glad we cleared that up. All right. Oh, I'm down to 10 minutes. That's surprising. Is this not a 1-hour session? So I don't think we're down to 10 minutes then. What's the consensus of the front row? How many minutes do you think we have left? 25. All right. Okay, so the lady at the back throws up her hands. So we're going to stay here for another 25 minutes. Unless I'm dragged off the stage. Okay. So the tunneling protocols. So there's lots of things you need to do with a tunneling protocol. And it turns out that every tunneling protocol that we have at the moment is falling short somewhere. So, for example, VXLAN is not very extensible. STT is somewhat extensible, but not very good for hardware. So we ended up creating a new tunneling protocol and calling it Genève. So the French speakers in the room will probably not appreciate my accent, but we named it after the French word for Geneva, and it actually stands for Generic Network Virtualization Encapsulation, and it's now supported by pretty much everybody that matters in the world of x86, and increasingly a number of hardware companies are also getting behind it. When I say supported, I mean they expressed their support by contributing to the draft where we documented this, and we believe that they're going to implement it. We've actually done a prototype implementation already ourselves. So tunnels, as I said, they're kind of a low-level detail. And if you looked at an NSX multi-hypervisor deployment today, you would see something a bit like this, where we have VXLAN tunnels going off to the hardware and STT tunnels going off to the hypervisor. And I use this analogy between a tunnel and a cable. Yes, it's important that you get the right cables in your data center. You know, you don't want to have twisted pair if you're trying to connect to an optical transceiver. But it's not the most important decision you're going to make in the data center. The same is true for tunneling. So we view tunnels as something that we can mix and match, and we'll pick the right one for the job, and we can change them over time because it's just a matter of software. So at some point, we'll probably start using Genève between hypervisors. And then at some later point, when the hardware starts to support Genève, we can start swapping out the VXLAN tunnels with Genève. But I want to be crystal clear on this. VXLAN is the protocol that all the hardware vendors support today. So if you're going to go and buy hardware switches and you want them to be able to communicate with NSX the way I've described, you should buy VXLAN hardware. Almost all the vendors support it, and you shouldn't be nervous about buying VXLAN because we will keep on supporting it for as long as there's VXLAN hardware out there. So VXLAN is what works today. Genève is where we see the future going. And as I said, it's a forward-looking talk. Remember the disclaimer from the first slide. This is what the packet header looks like. It wouldn't be a good networking talk without a packet header. So essentially, Genève is very similar to VXLAN, except it has this variable length options field. There's an internet draft that describes this in great detail, but the options are really the interesting part because that's what gives us extensibility. And this is something we've learned from many years of doing network virtualization, is that it's really great to be able to add a new feature in software and not have to wait for a new ASIC to show up in the hardware to implement it. So having the ability to extend the header and just make software changes gives us great ability to introduce new features. And we've been doing this for years with NSX using STT, and we're going to obviously want to do more of that in the long run using Genève. There's a lot of different things you could do with these options. I'll just maybe give you one example. That distributed router that I showed you, the ARP packets come from some vSwitch and go to some destination. When you reply to that ARP request, you want it to go back to the correct location of the place where the ARP request was originated. But the actual source of that ARP packet is not the place where you need to send the packet. It's the IP address of the logical router. It's not the physical device that generated the ARP packet. So you need to have some way of saying where this packet came from so that you can reply to the correct location. So putting a sort of a port identifier into a packet is a good example of something we can do with these options. I'll also say a little bit about service chaining. That's another thing that we can use this metadata for, because often when you are chaining services together, you want to pass information from one service to another, and a metadata header is a great place to do that. I think I said everything on this slide. Just want to again stress, we will continue to support existing tunneling encapsulations as long as there is hardware that requires it. So you shouldn't be nervous about this. This is just us thinking about the future, but we will be very clear on our support for VXLAN as long as there's VXLAN hardware in particular. All right, so service chaining seems to be a bit of a hot topic these days. So I want to talk about it just briefly. You see pictures like the one up the top there, where you want to take a number of services and chain them together. And there's a few aspects to this. There's creating the services in the first place. That can often be done by, say, spinning up a virtual machine that implements some services, or in some cases they might be services that are implemented natively in NSX, like firewalling and logical routing. So you have these services, you'd like to connect them into some kind of chain, or actually maybe a more complex topology, so really a graph of services. This is exactly what NSX does. NSX builds virtual topologies. So a service chain at its core is really just an example of a virtual topology. So while there's been a lot said and written about service chaining, a lot of the difficulties come in trying to build service chains in the physical world. But building service chains in the virtual world is actually extremely easy because we dynamically create topologies all the time. So if you want a service chain that looks like that, you specify that topology to NSX, it builds it. If you want to change the topology, you tell NSX to change the topology. It's very simple. So really, the most challenging part from our point of view is this idea of just being able to pass metadata along the service chain. Now, to give you an example of why you might want to do that, let's say that you did a very complicated classification of the packet somewhere in the service chain, and you'd like to take advantage of that classification later on in the service chain without having to sort of redo all of that complex classification. So you could do the classification here, write the result of that classification into a metadata field, and then carry that along with the packet. So when it gets to the far end of the service chain, you can do something special for that packet based on the earlier classification. So that's the sort of thing that Genève is perfect for. Pardon me. Here's a simple example of something that we can do today, even without having implemented Genève. We build topologies like this all the time. This is one where packets are going between two different subnets through a router and also hitting a firewall as they go from subnet to subnet. So that's the logical view of the topology on the top. Down at the bottom is the physical view, and you can see that we would simply send packets from the web VM into the vSwitch, through the distributed firewall, out to the physical network, across and back up through the other side. We can even do something a bit more sophisticated than that. You may have heard that we have an integration with Palo Alto networks. We're actually working with a large number of firewall vendors, and we're exposing APIs that enable third-party services to register with NSX to selectively receive packets. So in the firewall case, packets come from the VM, they hit our distributed firewall, and then three things can happen. We could drop the packet, we could forward the packet, or we could redirect the packet to a third-party service. And so you can now start to get very high bandwidth firewalling directly through the NSX capabilities in the hypervisor, but also selectively get much more advanced firewalling for a subset of the traffic by redirecting packets off to a third-party service. So this is a piece of functionality that's actually in NSXV at the moment, and it enables us to do some basic forms of service chaining already. And this is also really fundamental to our notion of being a platform that enables the partner ecosystem. We have a very large number of partners working on exploiting these APIs to add third-party services to NSX. All right, so the last topic that I'll cover before we go to Q&A is just, again, quite forward-looking. I want to talk a little bit about how we enable multi-site network virtualization. There are a few things that you can do today, and I just want to sort of quickly discuss those. There's actually a whole session that you can go to or catch it online 1974 is all about what works today in terms of multi-site network virtualization. But you can even do something that I think is really powerful today that we've done with some of our customers. Remember, I used the analogy to explain network virtualization in terms of server virtualization. Well, one of the really cool things about server virtualization is all the things you can do with a virtual machine that you could never do with a physical machine, like snapshotting it, like cloning it, like migrating it. These are all possible with virtual networks. We take snapshots of virtual networks, we capture all of the network state, and then we can clone that for testing purposes. We can migrate it to another place. For example, we took a snapshot of a running customer network, we moved it into our lab, we changed some configuration, we tested the configuration, we took a snapshot of that, and we sent it back to the customer and they put it into production. So they were able to get confidence that their configuration changes would work without ever touching their running network. So this is the kind of thing where I consider this part of what we enable with NSX, and you can see how you could use it for disaster recovery, for example. Take a snapshot of your network, back it up somewhere, and then in a DR situation, you can use the snapshot to completely recreate the network state that was in the primary data center. So lots of things that can be done today. But there's a lot of things that we would like to do that we're still working on. People often say, well, can you stretch a virtual network across 2 data centers? Well, yes, we can. But we don't like to do it in a large scale. So for example, stretching an L2 network between one data center and another raises all kinds of questions, particularly about how you get the traffic to arrive at the correct data center once you've now stretched a subnet across 2 different physical locations. It's fundamentally quite hard to solve that problem. So you also have to think about, if I had a virtual machine and I moved it across to a different data center while keeping it on the same subnet, where's the storage for that? So you have to think about your storage strategy as well. You can't just sort of think about stretching virtual networks. I mention this just because we often have people say, oh, I just love to be able to stretch my networks all over the place. And we generally say, you know, you should really think about the overall strategy, not just about stretching networks. So with that said, let me describe a couple of approaches that we're working on to enable a single NSX cluster to control multiple data centers. So you can think of there being a spectrum of possibilities. We have very widely dispersed data centers where we really have to do something sort of quite different because we have hundreds of milliseconds of latency separating those data centers and fairly limited bandwidth. And then we have situations, even in a single data center, where people are talking about maybe federating a few different NSX controller clusters so that they could have fault isolation. And then in between those 2 extremes is sort of metro-type situations where the latency might be fairly small, bandwidth is fairly high. So that's kind of the spectrum of possibilities. So if we start off on the wide area end of things, there's a technique that we're developing that we'll be able to use to enable us to federate networks where we have one NSX controller running in one data center and another NSX controller running in another data center. We'll be able to federate those controllers in a way that lets us create virtual networks that span multiple data centers. And we're going to do this leveraging some MPLS capabilities that are being put into the product. MPLS is a big topic, probably not too... Well, actually, let me ask, how many people here are MPLS experts? Okay, well, so you guys will totally understand this. For the rest of you, I apologize. I'll keep it quick. So we're basically going to use MPLS as a way of stretching or connecting virtual networks between 2 data centers. The idea is that we treat the boundary between 2 data centers as an inter-autonomous system boundary, and we advertise virtual networks using standard MPLS inter-AS techniques. So if you're an MPLS expert, you'll recognize some of the things going on here. RFC 4364 describes how this approach works. It's option 10B if you read the RFC, where we advertise logical network prefixes using BGP, and we associate labels with those logical prefixes. So what that enables us to do in a multi-data center environment is something like this. We can put one NSX deployment in one data center, another NSX deployment in a different data center, and we connect them using multi-protocol BGP. And now you can create a logical network over here, create another one over here, and then advertise them. And there's the 10-minute warning, the real 10-minute warning. So we advertise them using multi-protocol BGP, and now we can effectively stitch them together so that from either data center, the hosts or the virtual machines sitting in those data centers see the other virtual machines in other data centers as being reachable. I'd love to spend about another half hour going into the details on this, but obviously I can't. And then finally, I'll just very quickly talk about another way of federating data centers, or sorry, federating controllers. So if you saw me talk last year, you would have seen a version of this slide. The NSX Controller actually is a very sophisticated distributed system. I talked about it being logically centralized, but it's actually implemented across a number of different hosts. And all of the state that we have to manage, things to do with which logical network is where, which hypervisor is currently available, all of that state is stored in a distributed way across the nodes in the cluster. And we can make the cluster bigger, and we can spread the state out across different nodes in the cluster. So you can actually imagine taking a cluster like this and splitting it, and now you could start thinking about having that as a sort of a federated solution where one part of the cluster could be running one set of hypervisors and another part of the cluster could be running another set of hypervisors. Now once you've done that, there's still communication going across between the nodes in the cluster, but you can make that communication somewhat bounded. This is the sort of thing that you would do in a federated environment within a single data center or across data centers that are fairly close together with low latency, high bandwidth links. Obviously, this is just a sketch of an idea, and we've got a lot of work to do to bring this one into play. But I just wanted to give you a sense of we are thinking long-term here about solving a wide range of multi-site scenarios with NSX. So, to sum up, I didn't really cover this topic very much, but NSX is not something to be scared of. Network virtualization is becoming mainstream. You know, we're well over 150 customers now, so even if you're not currently playing with NSX, you shouldn't be scared of trying it out because it's becoming a much more consumable technology. It's going into small banks, it's going into companies like Starbucks and Best Buy. Physical networks, I spent a lot of time talking about that. You know, the physical network is important, and we don't want to underemphasize the physical network. Even as we are working to decouple virtual networks from physical networks, we also appreciate that physical networks matter. And so we're paying attention to that with things like the VTEP work and the elephant flow work. I talked a fair bit about tunneling. If you take away one thing about tunneling, I'd say it's great for networking people to argue about it, but it's not the most important thing. There's a lot more interesting things going on higher up in the stack where we think about adding services rather than worrying about exactly what the bits look like on the wire. But if you are at all concerned about tunneling from a perspective of should I buy my hardware or should I wait, the question should be resolved. It's perfectly okay to go and buy VXLAN capable hardware today because we'll be supporting it for a very long time. And then finally, I just very quickly and at a high level kind of sketched out what we're doing in multi-site just to give you a flavor of where that work is going and to give you some confidence that we're thinking about the future. So I think it's an incredibly exciting time to be involved in networking. I've been doing it for 25 years, and I don't think I've ever had as much fun as I'm having now. So I hope you folks will have some fun with NSX, and I thank you very much for your time. For questions. So before you leave, please fill out a survey, but only if you enjoyed the presentation. And if you want to stay for questions, please just try to raise your hand. There's a man at the back with a hand up. So for those leaving, try to do so quietly as we try to get the microphones to the people with questions. All right, I'll take the one in the front row here, and there's a man in the very back row with his hand up as well.
Hello. Yeah. Can I ask what security accreditation or testing has been done regarding NSX?
The question is what security accreditation or testing has been done with NSX. I wish I had a good canned answer for that. I know that we got One of the sort of well-known accreditations for our Edge firewall, which we've now implemented in a distributed way, and we're going through the same certification for it. But I'd have to take that one offline to get you a more solid answer. But I know we are working on accreditation. Okay, we have another question down here in the fourth row. I think the man who was at the back, did you just move? Was that? No, so anyway, if you're having trouble getting your question answered, you might want to move forward.
How many links you need between two data centers? Why don't can just use a technology like DWDM?
So the question is, what kind of links do we need between data centers? Just like within the data center, we're pretty agnostic about how you interconnect data centers. As long as you have IP connectivity, then we can work across it. Yeah, we've got the question over here.
Yeah, the question is that why are you using STT between hosts and not VXLAN?
So the question of why do we use STT between hosts and not VXLAN, and we don't always use STT, just to be clear, we sometimes use VXLAN, but we developed STT because it's an extremely efficient protocol for high bandwidth transfers, and so when we were first starting to do this, the overhead cost of tunneling was a big concern, and so we developed STT to dispel that concern. These days you can also do VXLAN at high speed, so we don't always use STT, but we still do like the extensibility of STT.
So if you choose a network interface card with VXLAN offload engines, then we can select.
Exactly. If you have VXLAN offload in your NIC, then you're in good shape.
Question?
Yeah.
Where would the vShield app fit in the picture?
I'm sorry, I didn't catch.
The vShield app?
Where's the vShield app fit into the picture? So the vShield app is a bit before my time, but if I understand, the vShield app was basically a centralized device that ran services. So today, some of those services are getting distributed, and some of them run in the NSX Edge. So it's getting blown up is a short way of describing it, I guess. But the capabilities continue to live on, some in distributed fashion, some centralized. Yeah.
What about data encryption between multi-sites?
What about encryption between sites? Yeah, so we do support IPsec encryption today to get us across long-haul links. And actually also SSL, I think, in some cases. So we do have a few encryption options for multi-site, and obviously that would be necessary for any kind of reasonable wide area multi-site solution.
Is that something going to be incorporating within NSX, or is it going to be a completely different way to encrypt it?
I'm sorry, I didn't quite catch that.
Is there a possibility to encrypt within NSX, or does it have to be the normal traditional way to encrypt the data?
I'm going to have to maybe take this one offline because I'm not quite getting the question. But you can see me at the end though. Sorry. Yeah, we've got a question over here.
So today you have two products for NSX. One is for vSphere and one is for multi-hypervisor. Do you envisage to join the two products to have a single one? Or?
Yeah, so it's a fair question. So we have two versions of NSX today, the vSphere optimized version and the multi-hypervisor version. And the question is, do we plan to merge them together? So I have to be careful how I put this, but yes, our plan is to have a single product that brings together all the features of the two platforms, which means multi-hypervisor support and all the sort of good L4 through 7 things that you see on NSXV.
Question about how does NSX relate to OpenFlow and SDN?
Okay, it's good to get that question out of the way. So how does NSX relate to OpenFlow? So we historically used OpenFlow for communication between the NSX multi-hypervisor controller and the Open vSwitch. As long as we continue to support multi-hypervisors, we will continue to support Open vSwitch, and so you'll continue to see OpenFlow being used to control Open vSwitch. We don't use OpenFlow between the NSX V controller and the VMware vSwitch. We only use it for talking to the Open vSwitch. It's another one of those things, it's kind of a low-level detail as far as we're concerned. The main thing is we have some control channel. Okay, one more question here.
Can you talk a little bit more about Geneve support in hardware?
Sorry, what, support for what?
Geneve.
Oh, Geneve support in hardware. Sure. So the question is, what's the Geneve support like in hardware? So Intel announced support in their NICs coming up I think later this year. It's on our blog that they announced it about maybe a month ago that there'll be NICs that will do Genève offload. I don't know if there's anything I can say publicly about switch support, but I know of at least 2 vendors who are putting Genève support into their switches. So we're expecting it to, to proliferate. We're down to the 1-minute warning now. So I'll maybe take one more question. Or not. Oh, we go. Last question over here.
Regarding the control plane support, that you said that only OVSDB is supported between the controller and the external Windows devices. Like EVPN and BGP won't be supported?
So the question is, what protocols do we support for talking to other devices? So we do use OVSDB for talking to third-party devices today. I could definitely see us using BGP to talk to other entities as well, because we have BGP support today in the edge. EVPN, I don't think we have any plans. I wouldn't rule it out, I guess. And I think with that I'll have to stop. Thank you for staying to the bitter end, and enjoy the rest of VMworld.